All right, let's get into it. Today, we are pointing our cosmic magnifying glass at one of the most dynamic and, frankly, one of the weirdest objects in our galaxy, the Crab Pulsar. This thing is an absolute powerhouse, a total mystery, and it's a direct link to a star that exploded 1,000 years ago.
So get this, we are looking at the ghost of a massive star that went supernova. An explosion so bright, it was actually recorded by Chinese astronomers way back in 1054 AD. It's sitting out there 6,500 light-years away near the tip of the southern horn of the Taurus constellation, and its remnant now powers the famous Crab Nebula. And you know, this thing is so important, it's one of just 14 pulsars whose signal was etched onto the Pioneer and Voyager plaques, as part of a map for any aliens out there to find their way to us. And the thing is, it's not quiet, it is still talking, sending these incredibly powerful signals right to our telescopes.
So first things first, what exactly are we dealing with here? Well, a pulsar is what's left after a huge star collapses on itself. It's an object so ridiculously dense that a single teaspoon of it would weigh billions of tons, and it's spinning unbelievably fast. As it spins, it shoots out these beams of radiation, kind of like a cosmic lighthouse, and every time that beam sweeps past Earth, our telescopes see a pulse. But the Crab Pulsar, it's not just any old lighthouse. Yeah, it sends out regular pulses, sure. But every now and then, it unleashes these things called giant pulses. And they are exactly what they sound like. These sporadic, absolutely mind-blowing bursts of energy that are thousands, sometimes millions of times stronger than its normal blip.
And you want to talk about energy, the brightness temperature of these giant pulses can hit 10 to the 41 Kelvin. I mean, let's be real, that's a number that doesn't even make sense. It's a 1 with 41 zeros after it. This is, without a doubt, one of the most luminous radio events we know of in the entire universe. It's an almost unimaginable amount of energy coming from a single tiny flash.
So here's the catch. Before we can even start to figure out what's causing these giant pulses at the source, we have to deal with the crazy journey those signals take over 6,500 light-years to finally get to us here on Earth.
Right, so imagine trying to read a sign on the other side of a field on a really foggy day. That is basically what's happening. These giant pulses have to travel through what you could call a cosmic fog. These turbulent clouds of plasma that exist out in deep space and, importantly, inside the Crab Nebula itself. This fog just scatters and stretches the signal, blurring the message before it ever gets to us.
In this fog, it isn't even consistent. Scientists have to correct for two main kinds of distortion, which they call scintillation. You've got diffractive scintillation, which causes these really fast minute-to-minute flickers, and then there's refractive scintillation, which causes much slower changes, making the signal seem brighter or dimmer over days or even weeks.
All right, so let's move on to the next clue here. Once scientists have used a bunch of math to basically defog the signal, they can start asking the really big question, is there a hidden message? Is there some kind of pattern to when these giant pulses decide to fire off? See, other weird signals we've picked up from space, like some fast radio bursts, actually show repeating patterns. So you gotta ask, right? Does the Crab Pulsar do the same thing? Is it ticking like a clock with these giant pulses, or maybe are they clustered together, kind of like earthquake aftershocks, where one might trigger another?
The way you figure this out is you test the arrival times of thousands of these pulses against two different ideas. On one side, you have a clustered process, where one pulse makes it more likely that another one is going to happen right after. And on the other side, you have what's called a Poisson process, which just means every single pulse is a totally independent, completely random event.
And here's the answer. After sifting through data from tens of thousands of giant pulses, the science is crystal clear. Over long periods, the Crab's giant pulses show no clustering, no secret rhythm, no hidden pattern whatsoever. They are, for all intents and purposes, fundamentally random. It's like rolling a cosmic die every single time.
Okay, so if the pulses themselves are random, that probably means the source isn't some simple, predictable little machine. So let's zoom out a bit from the pulsar itself and take a look at its immediate neighborhood, that chaotic, gorgeous mess that is the Crab Nebula.
It turns out that cosmic fog we were talking about isn't just sitting there. The Crab Nebula has its own weather. Seriously. It's this active, dynamic place with dense clouds of plasma swirling around and turbulence that gets stronger and weaker over time. And all this changing weather has a direct impact on the signals that have to punch their way through it. And we can actually see these seasons in the data. Long-term monitoring has shown these really distinct periods. For example, from 2002 to 2007, the nebula was in a quiet period, not a lot of disturbance. But then that was followed by a much stormier active period from 2009 to 2013, when that cosmic fog got a whole lot thicker.
And this stormy weather, it's not random either. It seems to be directly connected to the pulsar's own violent outbursts. Things like glitches, which are these sudden jarring speed-ups in the pulsar's spin, or massive gamma-ray flares, and just a constant stream of particles called the pulsar wind, all of it seems to be stirring the pot and changing the weather inside the nebula. Okay, and all of this brings us to a very recent and totally unsolved mystery. A sudden change in behavior that caught scientists who really thought they had this thing figured out completely by surprise.
Just look at this. In early December of 2022, the rate of giant pulses we were detecting from the crab just skyrocketed. It shot up to the highest levels anyone had seen in a 461-day observation period. It hung out there for a bit, and then it slowly died back down to normal over about 2 weeks. It's like the lighthouse suddenly started flashing like crazy.
Now here's what's really fascinating. It wasn't just the rate of the giant pulses that changed. The pulsar's overall average brightness, its steady background hum, also went way up during this event. So something fundamental about its entire energy output changed, not just its habit of shouting every now and then.
So what caused it? Well, the honest answer is, we don't know yet. But the leading theories are pretty wild. Maybe a super dense clump of plasma just happened to drift in front of the pulsar, acting like a cosmic magnifying glass. Or maybe there was one of those glitches in its spin that was just too small for us to detect, but it was enough to trigger this outburst. Or, and this is the most exciting one, maybe it's a completely new kind of behavior that we've just never, ever seen before.
What this all really means is that the crab pulsar isn't some static object in a museum. It is a living, breathing laboratory for studying the most extreme physics in the entire universe. We are literally watching a cosmic mystery unfold in real time, and every single new pulse, every new outburst gives us another clue to the puzzle. Which leaves us with a final thought. After nearly 1,000 years of shining, the ghost of this star is still finding new ways to surprise us. It's a pretty humbling reminder that even in the most well-studied corners of our galaxy, there are always more secrets waiting to be told, whispered to us in these giant, impossibly powerful pulses. What's it going to tell us next?